Everyone, I'm Surya, and this is joint work with Spencer and Vinod. And so today I'll be talking about adaptively sound zero-knowledge SNARKs for UP. So first I'll start by defining SNARKs. So in the SNARK setting, or a succinct non-interactive argument setting, we'll first fix a NP language L, and there's a prover that holds an instance X and a witness W. So the prover now has some prover algorithm, and he's going to generate some short proof pi, and so send over X along with this proof to the verifier, and the verifier should be able to run this verification algorithm on X and pi to figure out if X is in the language. And the goal here is that you want this pi to be much, much smaller than W. So you could just send over the whole witness, but we want some cryptographic object that lets you get succinctness. So this is not quite possible in the plain model, so we'll allow for a common reference string. So basically, I'm going to let both the prover and verifier algorithms run, take the CRS as input. And again, the goal here is for a pi to be short. So we need two properties. The first property you want is completeness, which basically says that if everything goes well, the verifier should accept. So if P has a valid witness and uses that, verifier should accept. And the second property you want, and for the purpose of this talk, we want adaptive soundness. So basically, I'm going to given a malicious prover P star, it's hard for him to come up with a cheating proof for X star not in the language. And I'll say this in symbols. So first, P star takes the CRS as input, and he needs to produce some X star pi star such that X star is not in the language, but the verifier accepts the pi star. So again, this is adaptive. So here, note that the P star can see the CRS before choosing X star. Okay, so in this talk, I'll be focusing on designated verifier SNARKs. So in this setting, I'm actually going to allow the verifier to also hold a secret state SK, and you can only verify a proof if you have SK on you. So, so the verification algorithm now depends on SK as well. But there's a little bit of asymmetry here because in the public setting, the prover could always check if its proof will be accepted. So in the designated verifier setting, what I'm going to allow is for the prover to reuse the verifier. So he can make many queries to the verifier and then come up with a cheating proof based on all these queries. So that's what reusable soundness means. So this is the target of this work. Okay, so what's the state of SNARKs today? So in the original work of Macaulay, and then followed by a sequence of amazing works, we've already had SNARKs for NP from the random oracle model on knowledge assumptions for quite a while. And then in using obfuscation or IO specifically, we've also had SNARKs for NP for quite a while. But if you go all the way down to LWE and other falsifiable assumptions, we have batch NP, P, NTISP, and so on. And the latest work of JKLV does NP intersect co-NP, but we're not quite at NP yet. So in the first two settings, we have NP. In the last setting, even in the designated verifier setting, we don't have NP yet. So the goal of this work is to make some progress towards this problem of constructing SNARKs from LWE or from not obfuscation, basically. Okay, so our first result is that we construct a designated verifier SNARK for UP, which is a subclass of NP that I'll define on the next slide, from LWE and evasive LWE. So before I define all the terms, I'll just give a big picture interpretation of this work. So big picture, there's LWE, there's obfuscation. And evasive LWE has sort of acted as this bridge between the two, in the sense that it has allowed for many constructions that were only known from obfuscation before, but not LWE. So evasive LWE has let us construct a bunch of things. So this is an assumption introduced by Hotak in this work, and where you construct optimal broadcast encryption in CPABE. And then there have been other constructions of witness encryption, NLIO, and so on. So evasive LWE has allowed for new lattice-based constructions of these objects that were previously only known from obfuscation. So in that sense, we should really view this result as a bridge. Hopefully one day we can use LWE instead. And I guess as a side note, this is also possibly post-quantum secure. Okay, so what is UP? UP, or you can think of this as unique P. I think it's more correctly unambiguous polynomial time. It's basically a subclass of NP where for every X in L, there's exactly one witness. So every X is going to have at most one witness. And just for something concrete to keep in mind, you can think of, for example, a very simple injective function. And using this injective function, you can define a language which basically says X is in the language if it has a pre-image according to this function. So this is an example of a UP language. Another example is factoring. So just by the fact that factorizations are unique, you can see that you can define a language N language where N is in the language if it's exactly product of two distinct primes, or two primes. So these are two examples of UP languages. So our work captures SNARKs for these languages. And then now the main tool that we use is evasive LWE. So what is this thing? So this is an assumption proposed by Hotek. This is kind of what it looks like. First fixed distributions S and P, and these are going to be possibly correlated. So S is a distribution over tall matrices, P is a distribution over wide matrices. And we're going to also have another matrix B, which is uniform and independent of S and P. Suppose we're able to prove something like this. We're able to prove that S times B plus Gaussian noise and S times P plus Gaussian noise, this looks pseudo-random. Then the assumption says we also believe that SB plus E, and if you replace the second term with B inverse of P, which is basically this object, which is, okay, so what is B inverse of P? It's a, give me 1 second. Okay. So B inverse of P is basically this quantity, which is a Gaussian pre-image sample conditioned on this equality holding. So what does this mean? It's like a matrix such that with small entries, such that B times this thing equals to P. How do I go backwards? Okay. Okay, this is fine. So what's the intuition here? So we knew that SP plus E basically gave no information about SB plus E. So now if I give you a Gaussian pre-image sample of B inverse of P, the hope is that all you can do with this is multiply SB plus E and B inverse of P. So what do you get when you do that? You get SP, because like the first term multiplies with B inverse of P and the B cancels out. And then you multiply the error term with B inverse of P. So again, B inverse of P is a matrix of small entries, so it still looks like noise. So the only thing you gain from multiplying them together is sort of this SP plus E term, which we already knew told you nothing about SB plus E. So that's intuitively what evasive LWE says. So this is the assumption we'll use. And we'll actually need like an auxiliary input version of this assumption, but I'll keep it simple on the slide. Okay. So the motivation for this assumption is that there are many lattice-inspired obfuscation schemes that fall into this so-called zeroizing regime, where you're able to collect many correlated equations. And the hope here is that because of this property that you have many uniformly random-looking equations, you actually can't do this so-called zeroizing attack. So yeah, this is where the assumption comes from. Okay, so I've basically explained the first theorem. So the second theorem of this work is that we construct a SNARK. So what's a SNARK? So say you have a prover who sends over an X to a verifier, but the verifier doesn't only want to know that X is in the language. He additionally wants to make sure that the prover has a witness. So you really want to argue that P must know a witness. So the way you would define this is through an extractor. So let's say you have an extractor. What the extractor can do is that he can use any prover that can make many proofs for this X to come up with a witness for this X. So what do? You send over a CRS, and then you get back a proof. And you keep doing this many, many times to collect many proofs. And the goal here is for the extractor to output some W such that X is RXW equal 1. So essentially, this is the way for you to say that if P is able to produce accepting proofs, I can also get a witness from this prover. Okay, so our second result is that assuming the polynomial hardness of LWE, as any SNARK for UP can be upgraded to a SNARK with a K for UP while preserving zero knowledge. So as a corollary, we get SNARKs for UP from LWE and evasive LWE. And I just wanted to point out here that the prior work actually does this from assuming a SNARK for NP. So our main contribution is that we upgrade UP to UP. And the reason why this is interesting is because SNARKs with a K for NP are known to be impossible in general through black box reductions. So in some sense, like this restriction to UP is necessary, and we actually get a positive result here. And just for a concrete example, let's say consider this like UP relation, which is basically X comma the factorization of X, right? So by the fact that factorizations are unique, X only has a unique witness. But also, if you look at this language, it's actually vacuous because every X has a factorization. So the cool thing is that using this argument of knowledge, you actually get some useful property about from the SNARK system, because now you actually can argue that such a prover actually knows a witness to this X. So in particular, it composes well with cryptographic objects, because now you can use, for example, the hardness of factoring as a through the SNARK for UP. Okay, so that's the second result. Okay, so the third result is that we make some progress towards overcoming the Gentry-Briggs barrier. So what's the Gentry-Briggs barrier? This is a very informal version of the barrier. It says that if you want to construct an adaptive SNARK, for a language that takes 2 to the n time to so-called decide, then there's no 2 to the n to the epsilon black box reduction to falsifiable assumptions for this. So that means you can't like reduce to like LWE or BDH or other falsifiable assumptions with a 2 to the n to the epsilon time reduction to get and also get adaptive SNARKs. So just to be make it clear what I mean here. So adaptive soundness means that first I see the CRS and then I choose my instance I will cheat on. In the non-adaptive setting, I choose my X star that I want to cheat on, and then I see the CRS, and then I come out with the cheating proof. So ideally, you want a SNARK in this setting here because it's more general than the non-adaptive setting. But there's been this like long-standing barrier against this because like we didn't think it was possible from falsifiable assumptions. So yeah, so this is like Gentry and Wicks like barring the adaptive SNARKs from falsifiable assumptions. Well, okay, there is still a password. There's still a way through, and it's an exponential time reduction. But we're not quite done yet because we still have to be quite careful to make sure the proof is not too big. So what do I mean here? So fine, okay, yeah, there were no adaptive constructions from falsifiable assumptions before 2024. And our work overcomes this by exactly doing what I said, which is to run a 2 to the n time reduction. But the problem is that it's not quite clear how to maintain succinctness while doing this, because if you run in 2 to the n time, then you have to set your security parameter to be like n, and then the proof size scales of the security parameter and it's n. So it seems like you need to be a bit more clever about how you do this argument. So in our work, we basically show that if you take any so-called Sahai-Waters-like SNARK, which is, so this is like a SNARK or NIZIC as was written in the original Sahai-Waters paper, and you make sub-exponential underlying assumptions, you can actually make it adaptively sound in the designated verifier setting. So take the construction as is, and it's actually adaptively sound in the designated verifier setting, while the proof size is still lambda bits. So so as a corollary, because our SNARK for UP actually follows the so-called Sahai-Waters template, it is actually adaptively sound. And a second corollary is that if you take the Sahai-Waters construction in the designated verifier setting, it's also adaptively sound. So this overcomes, the second corollary overcomes the Gentry-Wicks barrier because both assumptions are sub-exponentially falsifiable. But I'll say there are beautiful concurrent works by Waters-Hu, Waters-Zandri, which is like the next talk, which constructs adaptively sound publicly verifiable SNARKs for NP, additionally assuming either factoring, discrete log, or LWE. So here they actually need an extra assumption, which they removed in a new work. So they now have SNARK for NP from IO and 1A functions. But an interesting open problem is how to show the old Sahai-Waters construction is actually adaptively sound, because this is a slightly different construction than the original construction. Whereas in the designated verifier setting, we know that the Sahai-Waters construction is actually adaptively sound. So can we show that the Sahai-Waters construction is adaptively sound as is? It's an interesting open question. So, okay, I'll go over at a very high level what our UP SNARK construction is. So first I'll recap the Sahai-Waters SNARK template. So the prover is going to have the verifier will have a PRF key K, and the CRS will be an obfuscation of this program. So the program takes as input X and W. If W is a valid witness for X, I output the secret PRF value corresponding to X. If W is not a valid witness, I will not say anything. Okay, so the point is, if you have a valid witness, you can actually evaluate the program and run the program to get pi, and this pi will in fact equal to the secret PRF value. And the way you prove soundness is by saying, well, if X star is not in the language, the obfuscation hides this PRF value for that X star. Like, so the way Sahai-Waters does it is by instantiating this program with an IO and puncturable PRFs, but we're going to take a slightly different route to avoid IO. So the new tool we construct in this work from evasive LWE is what I'll call sigma PRF obfuscation. So using evasive LWE, we construct a new average case obfuscation notion for matrix program. So I'm being very hand wavy here. And it roughly has this following guarantee. So say you have this matrix program, you evaluate it on every single input, and you add some Gaussian noise to it. So that's what this EX term is. So let's say that, so in English, it says the function is a very secure PRF with added noise EX. So for every single X, you're going to add like a random noise. And let's say the precondition is that, well, okay, this truth table looks pseudo-random, even in the presence of this auxiliary input. So you cannot learn anything about this auxiliary input given the truth table. That's what the precondition says. Then I'm going to give you an obfuscation of this matrix program that satisfies that the obfuscation doesn't leak anything about this auxiliary input. So the obfuscation leaks nothing more than the truth table of the function itself, is intuitively what this is saying. So we build this from evasive LWE, and at a high level, we use GGH15 techniques, and we generalize the Vaikundanathan witness encryption construction to achieve this. And we use this obfuscation instead to get our Sahai-Waters-like SNARK. Okay, so high level of the construction. So first, we constructed the average case obfuscation notion. Then consider this particular function here. So W on input X and W is going to output one of two things. If W is a valid witness for X, I'm going to output a PRF value of X from the first PRF. If W is not a valid witness, I'm going to output G of XW. So it's a PRF on XW, but it's a different PRF than this guy. And now my claim is that this is a PRF with if R is a UP relation. The reason being, if R is a UP relation, then any element from F only appears once in the truth table. Whereas if it's not a UP relation, then you can actually break the PRF security of this thing, right? Because you can take two witnesses for any X and the corresponding PRF values should be the same. So it's only a PRF if the underlying language is UP. So this is where the fact that the underlying language is UP is important in our construction. And finally, all we're going to do is we're going to obfuscate this program and let the secret key be K1. So then you can argue that because the truth table doesn't contain PRF K1 of X star, right? Because X star is not in the language. This value is nowhere in this truth table. So therefore, you cannot learn this value from the truth table. So now if I give you the obfuscation of this program, you should still not be able to learn this value. So therefore, you can now replace like IO with this, replace IO with this average case obfuscation notion that I defined. Okay. So that brings me to the end of the talk. So I'll just summarize what I've said. So our first result is that we construct designated verified SNARKs for UP from evasive LWE. The second result is that we construct adaptively sound designated verified SNARKs via our adaptivity compiler that takes any so-called Sahai-Waters-like SNARK and makes it adaptively secure. So now we have adaptive SNARK for UP from LWE and evasive LWE, and an adaptive SNARK for NP from sub-exponential IO and one-way functions. And finally, we showed that we can actually upgrade our SNARKs to SNARKs for UP from either evasive LWE or by using this IO plus one-way function plus LWE approach. So that gives you a SNARK with the K for UP from falsifiable assumptions. So this is pretty cool because this overcomes the result 2 overcomes Gentry-Wick's barrier. And the second result gives you a positive result in the SNARK land, even though there's this like negative result saying you can't get SNARKs for all of NP. Okay, thank you very much.
Thank you, Surya. We have time for questions. If you would like to ask a question, there's a mic right over here. You can step up. Okay, so I'll ask a quick question. So you mentioned that you need like an auxiliary input version of the evasive LWE. Like, you know, for knowledge assumptions with auxiliary input, there are these like general impossibilities. Like where does evasive LWE stand? I see. So that's for the obfuscation and for the evasive LWE assumption per se. Mm-hmm. I see. I see. Okay, interesting. Thank you. Okay, any other questions? Okay, so let's thank Zoya again.
All right. Good. All right.
Okay. So the next talk is about adaptive security in SNARKs via I/O and lossy functions by Brent Waters and Mark Zandri, and Mark will give the talk.
All right, thanks for the introduction. So we'll repeat a little bit of the background from the last talk. So what is a SNARG? So a SNARG allows Alice to send a short proof of some NP statement to Bob, where again, the proof is much shorter than either the statement length or the witness length. And the model we're going to work in, again, is we're going to have a CRS, and we're not going to place any succinctness requirements on the CRS. So we only care about the size of the proof. The CRS can be as large as we want, as long as it's polynomial sized. So as discussed also in the last talk, there are a couple notions of security we might care about for SNARGs. So one is selective soundness. Here, the adversary chooses some false statement X, then gets to see the CRS, and then has to produce a proof pi for that X. But what we really want is adaptive soundness, where the adversary just gets the CRS and then can adaptively choose both the false statement X and the proof pi. So this is going to be our goal. So earlier this year, Waters and Wu gave a solution to adaptively sound SNARGs. So they show that there exists an adaptively sound SNARG for NP, assuming the following primitives: sub-exponentially secure indistinguishability obfuscation, sub-exponentially secure one-way functions, and then an additional assumption, which is they need essentially a perfectly re-randomizable one-way function. This can be polynomial secure. So where do we get these polynomially secure, perfectly re-randomizable one-way functions? Well, we can get them from discrete logarithms, from factoring, or from things called group actions, as long as they're perfect. But there's a noticeable omission here, which is we do not know how to get perfectly re-randomizable one-way functions from, say, learning with errors. All right, so in this work, we overcome this. And what we do is we give a adaptively sound SNARG for NP, assuming sub-exponentially secure I/O, sub-exponentially secure one-way functions. And then our additional extra thing that we need is no longer going to be a perfectly randomizable one-way function, but it's going to be a lossy function. It's going to be a lossy function that has to be very lossy. I'll give a little more sense of what I mean by very lossy. We have some technical terms in the paper. For this talk, I'll just keep things a little more informal. What using very lossy functions allows us to do, though, is we can actually instantiate this last line with LWE, and that's kind of the other main theorem of this work, is we get a lossy function that is very lossy from LWE. And I'll note that LWE actually has been long used to build lossy functions. However, the prior work did not satisfy the strong notion of lossiness that we need, and was actually, only rather weakly lossy in comparison. Okay, and as was also briefly mentioned in the last talk, there is some subsequent work that even just completely removes this last line and gets things from just sub-exponentially secure obfuscation and one-way functions. So this paper kind of is going to be the lost middle child in this line of work, but hopefully you'll find the talk at least a little interesting. Okay, and before I get into the actual meat of the paper, I just wanted to briefly talk about complexity leveraging. So complexity leveraging is often used to upgrade selective security to adaptive security. But in the case of SNARGs, you have to be very careful. So what is the typical approach to lift selective to adaptive security using complexity leveraging? It will look like the following. So we have some adaptive adversary that gets to choose X adaptively. And we're going to try to come up with a selective adversary that has to choose the statement that it attacks before seeing the CRS. How does it do that? Well, we're just going to have it guess a truly random choice of statement X prime. It gets the CRS, passes it to the adaptive adversary, and gets the statement and proof from the adaptive adversary. And the selective adversary in the middle, he's just going to hope that he happened to guess right in the first, in his choice of X prime. And if he does happen to guess right, then he actually will win, because he will be able to produce X and pi, which are a valid proof of a false statement. So there's a loss in this reduction. What is the loss? Well, it is just 1 over the total number of statements. And as long as we can actually prove that our selective sound SNARK is actually secure even with really, really tiny success probabilities, even, things that scale with 2 to the minus instance length, then we actually will get this proof to work and we will rule out such a adaptive adversary. The problem with this, though, is that in order to get this regime where we're even ruling out extremely tiny success probabilities, we need to, we need to assume sub-exponential hardness, but we also need to scale our security parameter to be large enough to handle this loss in the reduction. And basically, you need to scale the security parameter to grow with the instance size. But if we're scaling the security parameter to grow with the instance size, that means we're scaling all of the terms in our protocol with the instance size. And so we're actually going to end up blowing up the proof size, and we will no longer have succinctness. So the takeaway is that complexity leveraging isn't necessarily bad, and you could use it, but you have to be very careful. So basically, if you have a security parameter that appears in pi, that security parameter has to stay small in order to not ruin succinctness. And what that means is that you can't absorb losses that depend on the instance length. You could absorb exponential losses that are much smaller than the instance length, but you can't absorb losses that grow exponentially with the instance length. But what you can do is you can have two security parameters, let's say, one that affects the CRS size, one that affects the size of the proof. And the security parameter that affects the CRS size actually can absorb these giant losses that depend on the instance size, as long as the proof one kind of stays independent of the instance size. So that's going to be the overall strategy. This was also the strategy of the previous work by Waters-Wu, and our strategy as well is to just carefully play around with the security parameters of the various schemes and hope that we can get the reduction to work in this way. Okay, so let's start with the very high-level blueprint of what Waters and Wu do. I don't have nearly enough time in this talk to actually go into the details. But basically what they do is they have some obfuscated programs in the CRS. And these programs serve two purposes, right? So one, they allow you to actually prove true statements as long as you have a witness. And then they also let you verify the proofs. And using some obfuscation magic, what Waters and Wu do is they say, okay, let's take the real world where we have a CRS consisting of these obfuscated programs and some adaptive adversary that sees the CRS and produces a false statement X together with a valid pi. And what they do is they transform this into a different looking world where you basically have for every single instance, you have a pseudo-random instance of your one-way function. And these are all succinctly represented in the obfuscated programs that live in the CRS. But now on the right-hand side, we don't care about X being a false statement or not. We arrive at an adversary that's able to choose an X, which maps to one of these one-way function instances. And then the adversary also comes up with a solution for that one-way function instance. So there's a lot of details that actually go into this. This is one of the main insights of the paper, was how to map to this. And we're going to just kind of start from that step of their work. Okay, so again, we have all these one-way function instances and an adversary that chooses one of them and is able to solve one of them. And ideally, we would want to say that this is hard, but the problem is that there's exponentially many such instances, and so we can't really just guess which one the adversary is going to do without incurring this giant exponential loss. And I will point out that a lot of complexity leveraging happens in this step of the proof. Here, complexity leveraging is based on the number of statements. So you actually do get this huge loss in the reduction. But only the obfuscation incurs this loss, and the obfuscation only appears in the CRS, not in the proof. So using the complexity leveraging is going to blow up the CRS, as we said is okay. But I haven't actually used anything about the security of the one-way function appearing in the proof yet, appearing in pi yet. And so so far we can still keep pi succinct. All right, so our solution is going to be to use lossy functions to complete the proof. And we're going to need a strengthening of the usual notion of lossy function to something that in this talk I'll just call a very lossy function. So what is a lossy function? Well, it's a function or a family of functions that are sampled in one of two modes. In one mode, the injective mode, the function is just injective. It maps the domain to range and there's no collisions. On the other hand, in the lossy mode, the function is very lossy. It maps the domain into a very, very small set, much smaller than the size of the domain. And a lossy function guarantees that the injective and the lossy modes are indistinguishable, despite being very different functions. So for a regular lossy function from the literature, we normally just ask that in the lossy mode, the size of the image is negligibly small, or is the ratio of the image size to the domain size is super polynomial. But we're going to require something much stronger. We're going to require that the lossy range size is actually some fixed exponential in the security parameter, but importantly independent of the domain size. So you can set the domain size to grow as big as you want, but the image size is going, in the lossy mode, is going to stay this fixed exponential in the security parameter, independent of what the actual input is. Okay, so how do we use lossiness to complete the Waters-Wu approach? Well, what we're going to do is using obfuscation magic again and using lossy functions, very lossy functions. We're going to take the setting on the right where all of the one-way functions instances are basically pseudo-random, and we're going to map it to the case where there's actually very few one-way function instances and they're kind of repeated many times. Basically what happens is the one-way function instances are derived from the range of the lossy function. And so the number of different one-way function instances you get on the other side it grows with the number of image points in the lossy mode of the lossy function. Okay, so we use lossiness to move to this setting where we have very few instances. And now we can actually just guess what instance which one-way function instance the adversary is going to select. We can't guess what x the adversary is going to select because that will incur too large of a loss. But we just guess which one-way function instance the adversary selects. The loss of this is the number of instances of the one-way function, which is just the lossy range of the lossy function. This is again a fixed polynomial in the security parameter. And so to absorb this loss, we only need to set our security parameter for the one-way function to grow with whatever this fixed exponential is, rather than growing with the instance size. So this is why we need this very lossy feature of the lossy function, because basically the input to the lossy function is going to be x, which again is huge. And so we need to be able to have this large input but keep the total number of one-way function instances small. Okay, so that's kind of the sketch of how we complete the Waters-Wu proof to get things to work without using their perfectly re-randomizable one-way functions. And so for the rest of the time, I will just talk about how we actually realize the necessary lossy functions from LWE. So what we're going to do is we're going to start from an existing blueprint for lossy functions from LWE. We'll see what the issue is, and then we'll fix it. So here's how you construct a lossy function from LWE. So your input is going to be interpreted as a short vector. And the key for the function is going to consist of this matrix A. And what you do is you just compute A dot x, mod some modulus, and then you do a sufficiently coarse rounding. And then the result of that sufficiently coarse rounding gives you your output. In the injective mode, A is full rank. And for an appropriate choice of parameters, you can actually show that this results in an injective function. And now what about lossy mode? So in the lossy mode, what we're going to do is choose A to not be a uniformly random full rank matrix, but we're going to choose it to look like at the top of the screen there, where A is basically very close to a low rank matrix. So it's the inner product of a tall skinny matrix with a short wide matrix, so that's going to be a low rank matrix. And then we're going to add some small Gaussian noise. So why does this work? Well, if you take if you take a dot x and you expand out the definition of a, you get this thing here. There's one term here that's this low rank matrix dot x, and another term here that's the error dot x. But x, remember, we're saying the input is a short vector, x is short, times some short matrix. So this thing over here is small. And the hope is that the coarse rounding that we apply to that just eliminates the error here, and we're left with just this term here, the low rank matrix dot x. But because this matrix is low rank, we know that the low rank matrix dot x lies in a very small span, right? It's just whatever that vector will lie in whatever the column span of what I've called B on the slides here is. And there just aren't too many of these, right? But the width of B is basically the security parameter. And so the number of these vectors here is just 2 to the security parameter, 2 to the poly security parameter. So in the lossy mode, we get that the number of images is just 2 to the it's just a fixed exponential in the security parameter. And I didn't discuss indistinguishability on the slides, but that just follows trivially from LWE. Okay, the problem is that this sketch doesn't quite work as I've described. And the reason is that if this term here happens to be very close to one of your rounding boundaries, the error that you get here can actually move you over a rounding boundary. And so for some inputs, this error term actually will affect the output. And if you look at what happens, you actually, even if you're usually very far from a rounding boundary, there are a vast number of points. They're very sparse, but there's a vast number of points that are actually very close to a rounding boundary. And when you're close to a rounding boundary, then the result of rounding will actually contain more information about your input, and you won't be as lossy as you hoped for. So it turns out you can still get some amount of lossiness from this, but you're not going to be truly independent of the input size. So we give a relatively simple solution to this problem. What we say is, well, what I'm going to do is I'm just going to stay away from rounding boundaries. So I'm going to take I'll end up having multiple matrices. I'll start with the first one. I'll look at, if I take A1, multiply by X, am I close to a rounding boundary? If I'm not close to a rounding boundary, then I know that in the lossy mode, rounding actually will eliminate the errors. And so I'm happy. Then I actually get the lossiness I want, and I'll output the result of A1.x. If A1.x happens to be close to a rounding boundary, then I'm like, oh, no, I can't do that. And so I'll move to A2, check if A2.x is close to a rounding boundary. If it's far, then I'm happy, and I output that, and I just keep going. And what we show is that you only need a polynomial number of matrices, but before you actually are almost certain to have one of these get you far from all the rounding boundaries. And so this blows up your image size a little bit, but it's small. It's just a polynomial which can be easily absorbed in the exponential terms in your image size. So the result is that we get the number of images are actually a fixed polynomial in the security parameter independent of the length of the input as desired. Okay, and that's my talk. Thank you.
Thanks, Mark. Any questions? Yeah, okay, you went outside, not to the mic. Okay, so any other applications to these very lossy functions? Can they take the place of elves, let's say, in some applications?
Possibly, yeah. So I guess the thing is with if you wanted to use like extremely lossy functions, there you actually need like exponential hardness. We're only looking at sub-exponential hardness. It's possible you could like push things to like almost exponential, like 2 to the n over log n. It's not something I've really thought about, but you might be able to get some sort of stand-in for else. Probably not all the way because I don't think have true exponential hardness for LWE, but you might be able to get close.
Okay. Okay, so let's thank Mark again. A quick announcement before the next talk. If you lost this phone, then come to me after the session. Okay, so the last talk of the session is about zero-knowledge IOPs approaching witness length by Noga Ronsvi and Mo Weiss, and Mo will give the talk.
Thanks, Neil. So this is not about SNARKs. This is about an information theoretic object called IOPs, which can actually be used to build SNARKs. So it's like a prequel to what we've just heard. And this also needs to be turned on, or? Okay. So what are these information theoretic objects? They're interactive oracle proofs, or IOPs. And this is an interactive protocol between a prover and a verifier. And the goal here is to prove, it works in the reverse order. The goal here is to prove that that X is in some NP language. And this is executed in rounds, where in each round, the verifier sends over a random string and receives a long oracle message from the prover, which she doesn't even read. And then once the interaction ends, then the verifier probes few locations in these proofs and reads just these locations. So, it might seem like a weird model to consider, because why would you want to talk to someone who's not listening? But from my experience, it's a pretty accurate description of talking to a 6-year-old. So this is my motivation to study IOPs. So in the end of all this entire interaction, the verifier decides whether she accepts or rejects. And the guarantees are that if X is in the language, then the verifier will accept with high probability. And if X is not in the language, then for any prover that can be unbounded, the verifier will reject with high probability. And you might be familiar with a special case of IOPs called probabilistically checkable proofs, or PCPs, where the verifier doesn't send any messages and the prover just sends one oracle. And as I said, these IOPs are motivated because they can be used to construct succinct arguments, and PCPs have important applications to hardness of approximation. So these are IOPs, and today I want to talk about zero-knowledge IOPs, which are IOPs in which the verifier learns nothing except the fact that the input is in the language. And this is formalized in the simulation-based paradigm, comparing the real-world execution to an ideal execution with a simulator. And we want zero-knowledge to hold against malicious verifiers that could potentially make many more queries to the proof compared to the honest verifier. So this is what happens in the real world. In the simulation, the verifier interacts with the simulator, so she sends over her messages, but the simulator doesn't have to generate these oracles. Instead, only when the verifier makes a query, then the simulator needs to simulate just the answer to this query. And in the end, we want the real and simulated views to be indistinguishable. So just a few comments. The first is that proof generation has to be randomized if we want to get zero-knowledge. And unlike standard zero-knowledge proofs, where we're used to thinking of getting zero-knowledge against any efficient verifier, here we can't hope to get it, because a polynomially bounded verifier can just read the entire, all of the prover messages, and then she'll learn something about the witness. Instead, what we want to have is information theoretic zero-knowledge against any verifier that could be malicious and computationally unbounded, but she's only restricted in how she accesses the proof. She can only access T symbols from the proof, and this zero-knowledge parameter T is a very important parameter of zero-knowledge IOPs. And if standard IOPs are motivated for the construction of succinct arguments, then zero-knowledge IOPs are motivated by the construction of succinct arguments that have black box zero-knowledge. So what do we know about these PCPs and IOPs, specifically in terms of the proof length? So there are two parameters here that we want to reduce. One is the proof length, and the other is the query complexity. So how many queries you have to make to verify the proof. And for PCPs, the proof length has been consistently decreasing. And we now have, so we have linear length PCPs that can, but to verify them, you have to make a super constant number of queries to the proof. For IOPs, the situation is better. So we actually have IOPs that have linear length and can be verified with a constant number of queries. Actually, we even have IOPs that have length whose length approaches the instance length or even the witness length. So this means the length is 1 plus delta for an arbitrarily small constant delta times instance or even witness length. So IOPs improve over their PCP counterparts in terms of these parameters. What about zero knowledge PCPs and zero knowledge IOPs? So despite almost 30 years of research, we don't have zero knowledge PCPs with linear length. And actually, each of these ZK PCP constructions have their own issues. For zero knowledge IOPs, the situation is better. We do have linear length IOPs for NP-complete languages, but still no ZK IOPs approaching the witness length. So 1 plus delta times the witness length. Even if you just care about getting zero knowledge against the honest verifier, we don't have them. And today I want to show you a construction of ZK IOPs approaching the witness length. So what we show is that for every constant delta, 3SAT has a ZK IOP whose proof length is 1 plus delta times the witness length M. So really approaching the witness length. And zero knowledge is against a verifier that makes M to the epsilon many queries for some constant epsilon that depends on delta. And actually we get good parameters in other, also other parameters. So the ZK IOP can be verified with a constant number of queries and with decent running times for the prover and verifier. So compared to what we had before, if you cared about the proof length of IOPs, we did have IOPs approaching the witness length, but they didn't have any zero knowledge. If we focus on zero knowledge, there are linear length ZK IOPs, but here there are two things to notice. So one is it's linear length compared to approaching the length, and also linear in what? So these IOPs are linear in the instance length. And for 3SAT, this could be even quadratic in the witness length. So this is our main result. And to get it, we give new constructions of the two main building blocks of IOPs and PCPs. We give new constructions of tensors of zero knowledge codes, and we give a new Samczyk protocol that has zero knowledge and sublinear communication. And these building blocks are so fundamental to the construction of PCPs and the IOPs that I think they're interesting in themselves. Like, I don't think of this as a means to an end. So let me tell you a little bit about how we construct our ZK IOPs. So let's start with, forget about zero knowledge. We don't care about the proof length. How do you prove that a 3CNF is satisfiable? So usually this is done in two phases. The first phase is an encoding or arithmetization phase, where the prover encodes the satisfying assignment using some code. Usually this is the low degree extension, the LDE encoding. And this he sends over to the verifier. And then in the second phase, the verifier checks that this witness is a satisfying assignment. And to do this, she exploits the structure of the LDE encoding, and she can use a Samczyk over the LDE encoding to check that W is a satisfying assignment. So this is how you get IOPs for 3SAT. And if we care about the witness length and we want to approach the witness length, then Ronsky and Rothblum showed in 2020 how to take this blueprint and reduce the proof length. And their first observation is we can't use the LDE encoding because it has super constant size. So instead, they use a high rate encoding C. So we're replacing all of these W hat, all of the LDE encodings with this high rate encoding C. But now we have an issue because this second step, the verification step, crucially relied on the structure of the LDE encoding to verify that W is a satisfying assignment. But now the verifier doesn't have this W hat. Instead she has this high rate encoding. So what they show is this beautiful code switching technique. They show that you can actually emulate a subcheck over the LDE encoding using any encoding of the message using a tensor code. And they give this, they use this code switching to give a sublinear communication subcheck over the LDE encoding, but using the high rate encoding that the verifier has. So this is their protocol. They use a high rate encoding, and then they use the code switching to emulate the subcheck over the LDE, but using the high rate encoding. So now we want to add zero knowledge to this. And the first step would be to replace the high rate code with a zero knowledge high rate code. And the second step would be to replace this sublinear communication subcheck with a zero knowledge sublinear communication subcheck. And I want to tell you a little bit about each of these components, starting with a high rate code. So the way in which we build these high rate codes is by taking tensors of zero knowledge codes. So I'll tell you a little bit about what tensor codes are and a little bit about what zero knowledge codes are and how we combine them. So what are tensor codes? So it's an operation you perform over some number of codes, and these could be general codes. And in our work, we consider tensors of any number of codes and any codes. But for the purpose of this talk, let's just think of tensoring two codes and not any codes. Think of polynomial codes. So Reed-Solomon or Shamir sharing, however you feel comfortable thinking about this. You take your message and you encode it, interpolate it into a low-degree polynomial. So when you take two low-degree univariate polynomials and you tensor them, what you get is a low-degree bivariate polynomial. More generally, if you have two codes and you tensor them, you think of the message as a matrix. You first encode each column using the column codes C1, and then you encode each row that you got using the row code C2. And the property that you get is that each column in this code word belongs to the column code, and each row belongs to the row code. And these tensor codes have many, many applications. Today, I want to talk specifically about tensors of zero knowledge codes. So what are zero knowledge codes? These are codes that are associated with a randomized encoding function and have this property that any T code word symbols reveals nothing about the message. And actually, tensors of zero knowledge codes are super useful. You've probably used them. You've just not given them this name. Because if you think of bivariate Shamil, for example, then what you're doing is tensoring Reed-Solomon, tensoring Shamil. And this is used in VSS, MPC protocols, really in many, many places. And today we ask, how does tensoring affect zero knowledge? So say, in particular, does tensoring preserve zero knowledge? If I have two codes, C1 and C2, they have T1 and T2 zero knowledge, what type of zero knowledge does their tensor product have? And recall that zero knowledge codes have this encoding function associated with them. So I'm not going to explicitly define it, but the encoding function that we consider is very natural. This is what you do when you Shamil secret share. And this is also the encoding used by a previous work by Boutel et al. On tensors of zero knowledge codes. And what Boutel et al. Show is that if you tensor two codes, you get zero knowledge against the minimum between the two zero knowledge parameters. And they ask, can this bound be improved? In particular, can we get zero knowledge against the maximum between the two zero knowledge parameters? And what we show is that, yes, we can. We can get zero knowledge against the maximum between the two zero knowledge parameters because actually we get something more general. So you get zero knowledge against adversaries that read T1 full rows or T2 full columns. And if you ask yourself, why do I care about these rows and columns? Well, this is what we'll need in the ZKIOP construction. But more generally, this is what we care about. Again, think of bivariate Shamil. The secret shares are rows and columns of this tensor product. And actually, our results are even more general than this, and you can look at the paper to find out. So this is what we show. You get zero knowledge against rows and columns. And think of reading, let's say, T1 rows. You're reading T1 times T2 symbols, but they're highly structured. So naturally, we ask, okay, can we get zero knowledge against reading T1 times T2 arbitrary queries? And here the answer is no, unfortunately. And I'll leave you with a little bit of a cliffhanger, go see the paper for details. So this is the first component, tensors of zero knowledge codes. In particular, we get as a corollary that there is a high rate code that is zero knowledge against adversaries reading rows and columns of the code word. And the second component is the sublinear communication zero knowledge sum check. So starting with standard sum check, this is a super influential protocol that lets you check that some message sums to alpha over a field by just making one query to its encoding in a tensor code. And this, the sum check protocol underlies many IOP and PCP constructions. And the zero knowledge variant of IOPs, of the sum check, underlies many ZK IOP constructions. So zero knowledge here means that you can simulate the view of the verifier, but by just making a few queries to the code word C itself. And the way in which these sum checks work is that they take the original code word, which is highly structured, and they mask it with a uniformly random code word. So you get something which is almost uniformly random. And then because this masked code word is almost uniformly random, you can run standard sum check over it and not reveal any information. But the problem with this is that the first prover message is this random code word, which is as large as the code. So this would not give us sublinear communication. And if we plug this into our ZK IOPs, the total communication would be at least twice the witness length. So if we want to get sublinear communication zero knowledge sum checks, we have to do something different. We have to somehow shrink the mask. And the high level idea of doing this is instead of just using sum checks as a black box, let's look at a specific sum check protocol and let's see what information it reveals. And let's tailor the randomness to hide this particular information. And this is indeed what we do when we use the sum checks of Ronsby and Rothblum. One caveat is that our sum check does reveal more information. It reveals full columns of the code word. But recall that we've shown that tensors of zero knowledge codes have zero knowledge against reading full columns. So that's fine. We can still get zero knowledge IOPs. Okay, so I want to tell you a little bit about this shrinking the masks. And for this, I need to tell you very briefly what Ronsby and Rothblum do. So very, very briefly and very, very simplified. You start out with some tensor code word. And the first thing the prover does is it sums up all the rows of the tensor code and sends this over to the verifier. And then the verifier also reads one column. So what does she learn? She learns one row and one column. These are two code words in the base code. And if we look at what type of information is revealed, so you take your structured code word and you kind of squish all the information down to this sum. You take the code word and you kind of restrict the information into one column. That's not too much information. So the idea is that if you only learn code words in the base code, what we can do is we can mask with a mask in the base code, which is much, much smaller than a full code word in the tensor product. So this is our protocol. I know you can't, understand it from just a few moments, but I do want to make two comments or like two things to notice. So the first is that this is the original sum check by Ronsby and Rothblum. And this is our randomization. So you see we mask in the base code. And then the verifier can somehow locally expand this mask in a way that will hide the column that she reads. So this gives us a sublinear communication zero knowledge sum check. And the way in which we get it is by using a mask in the base code. But this sum check reveals columns of the code word. When we combine it with our results of the first part of the talk, the fact that there exists a high rate code that is zero knowledge against reading columns, we get the first zero knowledge IOPs approaching the witness length. And I'll just remind you that this high rate zero knowledge code was a corollary of more general results that we have on tensors of zero knowledge codes. So you can read all about it in our paper. Thank you.
More. So maybe time for one quick question because the next session is starting soon.
You limited the adversary to a certain amount of queries. Does this process get easier when you limit the queries per round? So because that would still make sense in the compiler, right?
So I'll have to think about it, but I think that not really, because what happens is you start out with, say, a code word, and then the next round would be just continuing recursively with a one column, which is itself a tensor, encoding in tensor code, and then continuing recursively. So you have, the everything you have in the beginning. You have the code word itself, and you can just send queries to that.
Okay, thank you.
Okay, so let's thank Mo and all the other speakers again. And the next session will start soon. You're welcome to switch tracks if you'd like. And again, there's a